A telescope is, well, tele comes from the root word for distant. Telescope, telephone. Phone means sound. You're getting sound from far away. You can hear something from far away. A scope means to view something. So a telescope allows us to see far away. Over time, telescopes were built that could see all of the electromagnetic spectrum. We have optical telescopes with lenses. Galileo took a telescope design from some Danish guy and built one of his own and turned it towards the sky and looked out there, and he was the first one to look at these objects out there. Since then, we have developed telescopes that can look in all of these spectra here. So the radio, microwave, X-rays, ultraviolet, and everything. Here is a representation of the fact that our atmosphere absorbs a lot of these rays, and so we can't see from the ground. We can't see these rays, and the brown represents things are being absorbed. Most of the infrared spectrum is absorbed by the atmospheric gases. So anywhere where there's a hole here, we can see visible, and we can see a lot of radio waves. But these other ones, we don't see these. We have to get above the atmosphere. So in other words, it took the space age for us to build spacecraft that could detect waves that were being absorbed originally by the Earth's atmosphere. We had to build spacecraft that could detect certain waves, send them up into space, put them in Earth orbit or beyond, and so that they could detect these things, and then we could look at all of space in all of different waves. Here's another picture of the same kind of thing showing the different absorption through the atmosphere. All right, so let's talk about, briefly, optical telescopes and how they work. I'm going to give a brief summary of that. And optical telescopes work on refraction. Refraction is when light passes from where speed of light is faster into a medium where the speed of light is slower. This is in air or space or something like that, and it goes into, in our case, we're talking about glass. And when light enters glass, the light travels a little bit slower. Now that's not exactly true. The light travels the same that it always did. What they mean by traveling slower is that there's more interaction on the inside as it bounces around a bit and comes out the other end. It appears to have been going slower. That's what they mean. For our purposes, it's going from faster to slower. Here comes my incident ray, and I've drawn this line here. This is my surface. This is my boundary. I've drawn this line here. This is my surface normal. And it's just a line that's perpendicular. This line is perpendicular to the surface. That's all it means. When light comes in and enters the glass and it goes into a medium that the speed of light is lower, it will bend towards the surface normal, so that this angle here is greater than the refraction angle here. That's what happens in refraction. When it moves to a medium with a slower propagation speed, the light bends towards the surface normal. In the opposite direction, it would bend away from the surface normal. Here's my drawing that I just gave you. Here's the incident ray. It's going into, in this case, water. It bends towards the surface normal. It would appear to go this way, but it doesn't. Here is just the opposite. Here's a fish. And the fish, light is bouncing off the fish. As it rises up through the water and gets to the air, it's going from a lower speed of light into a higher speed of light. It bends away from the surface normal. You can remember this by, if it's going from a lower one to a higher one, the speed of light is higher, then the angle increases. It's higher speed, higher angle. Previous one was a lower speed, it's going into a lower speed, it's a lower angle. That's how you can remember it. So what this means is that if you're up here and you're trying to catch this fish, maybe with a spear or something, you see the fish down here. Because see, this is the direction of the light ray. So you think the fish is here, and yet the fish is actually there. Do you remember that movie Castaway that we talked about with Tom Hanks? And he had the analemma in his cave. Well, I don't know if you remember it. Go back and watch the movie. But at the beginning, he's trying to gig some fish, and he kept missing them. He kept missing them. And the reason is because he's looking here, and the fish isn't there. It's closer to them. So if you ever go gigging for fish, aim a little closer to your body because they're actually physically closer to you than you think because of refraction. So what does refraction do for us? Well, we can build lenses. There are lenses. And we have the convex lens and the concave lens. What happens in a convex lens? Briefly, as the light enters the center of it, it's going to go straight through. As the light ray comes and hits this point, here's my surface normal. As it hits this point, it's going to bend towards the surface normal, which means it's going to bend that way. And here's the surface normal on the other side. As it goes from the lower speed of light, medium, to the higher one, it's going to bend away from the surface normal, which means it's going to bend even further. So in other words, all of these light rays are bent towards a focal point is the idea. And what does this do? Well, it helps magnify objects. And this is a converging lens. You can see that the light rays are converging to a point, and we call this a convex lens. The other one is the concave lens, and just the opposite happens. As it enters the glass, there's my surface normal, it's going to be bent away from the surface, towards the surface normal, and as it reaches, it's going to be bent away, so the light rays are going to come in and they're going to spread out. And this is a diverging lens. Why am I telling you this? Is this a test question? Could very well be. And this is the concave lens. All right, so how do you remember these? How can you remember which one's which? Well, how can you remember if it converges or diverges? Which one is a converging lens? Which is the diverging lens? Which one is the concave? Which one's the convex? The concave lens has a cave in it. See, it's caved in. The concave lens, here's the cave, and you can see that it's caved in. The convex lens is the other one. It's as simple as that. It's the other one. You have two. All you need to know is the one. The convex lens is the other one. How do you remember which one is the converging lens or the diverging lens? Well, you can see that in a convex lens, the lines come together and form an X here. They're converging and forming an X. And there's an X in convex. The concave lens is the other one. It must be the diverging lens. That's how you can remember it. As simple as that. Reflection. When we talk about reflection, here's my surface normal again. Here's my surface normal. My angle of incidence, when my light ray comes in, it bounces off a flat mirror. It's going to bounce off at the same angle that it comes in. It's the same angle here. That's the law of reflection. What's a law? A law is a mathematical relationship that we see in nature to occur again and again. The law here is that the angle of it's very simple. Angle of incidence equals the angle of reflection. Very simple. But if we were to use this on a concave mirror, if we were to make a mirror that's curved like this, we can have light come in and it's all bouncing off at the same angle that it's coming in at. And we can make that go to a point, make it focus to a point. And this point that happens is the focal length. We can use this to magnify objects. We can use this to make telescopes. It's the basis for a reflector telescope. So a basic optical telescopes, we have refracting, we have reflecting, and we have a Cassegrain, a catadioptric. More specifically, here is a refractor telescope. We have a very large objective lens at the front. It comes in, it's objective lens. What kind of lens is this? It's a convex, it's focusing it. The light comes down, crosses itself, and it starts to spread out again, and there's another convex lens that straightens it out again. And the length of this focal length here, that's the magnification power. So if you want more and more magnification, you need a larger, longer telescope. And then this is a refractor. The light comes in, it bounces off the primary spherical mirror, and this length here provides the magnification. The light hits this secondary mirror here, it's flat. All this mirror here does is bend it up that way, and then we can look at what's in the mirror with an eyepiece there. And the magnification comes from this length here. So, and then the Cassegrain type is one where the light comes in. Here's a prime focus. This is a reflector telescope. Light comes in, bounces off a spherical mirror, comes back, and you could have somebody there and they could look at it directly. Newtonian, named for Isaac Newton, he invented this. Light comes in, we just looked at this, the light comes in, bounces off a flat mirror, comes out here and we can see this. A Cassegrain, the light comes in, bounces off a mirror that is flat that way, and then we have an eyepiece here and we're looking at that mirror and we can see the magnification that way. Well, Mr. Todd, if we have something in the middle of the telescope, why don't we see it? Is the middle of it just blocked out because we can't see anything? Well, no. The reason is because as this light wave comes in, remember this is coming in on either side. It passes through this thing and it's focused towards here. So you can see that, yes, there's a blank spot here, but it doesn't matter because it's taking the light that's around it and it focuses it towards here. What we're looking at is the reflected light from here that's bouncing on here. So we don't see a missing piece. There is no missing piece there. It's just not there because it's focusing all of this light that is hitting it onto there. So we don't see a big blank spot in the middle of our screen. So this next bit, great test questions. Why are large telescopes all reflectors? Why do we want to make a large telescope? The larger we make our telescope, then the more we can see. Remember, it has to do with intensity. Let's go back to intensity again. If I have a reflector telescope, here's my reflector telescope of this size, I'm gathering this much light, and 10 inches, something like that, a 10-inch telescope. And then I've got one of those large ones at the observatory, and this is, say, 10 feet in diameter. Okay. Remember intensity? Intensity is how much light am I gathering over a certain area. Well, here, if it's a 10-foot diameter, I'm gathering a lot more light than I am with a 10-inch telescope. If I'm gathering a lot more light, when I look at this, I can see more detail, is the point. With a larger telescope, the larger I make my telescope, the more detail I can see. So, and to make a larger refractor telescope, what do I need to do? I need to do the same thing. I need to make a huge lens out front. Well, that becomes, the larger that telescope is, the more and more difficult that becomes. Because to make a lens that large, you have to make it just right. It has to be perfect. And that's difficult to do. So this slide here sounds like a great test questions here. Why are large telescopes all reflectors? What is the advantage of reflector telescopes over a refractor scope? Lenses produce chromatic aberration. Light of different wavelengths come to focus at different points. What we mean by that, here is my lens. The light ray comes in. Remember, as light, you've seen this, as light comes into a prism and it comes out the other side, what happens? You see a rainbow. You see red and blue and green coming out. You see this big rainbow. Well, the same thing is going to happen with this lens here. When it comes out to the other side here, you're going to see some red, not being bent as much, on the edges of your object, and a little bit of blue. So you see that. Well, astronomers don't like that. They don't want to see that, especially if you're trying to study what's the true color of something. And so on a refractor telescope, you get this edge effect and a little bit of a rainbow effect around the edges, and you don't really want that. So we don't like that. When you make the next one, why are reflector telescopes, why are the larger ones all reflectors, is because mirrors only need to be configured on one side. If I'm making a reflector telescope, I only need to make this one side the best. I only have to polish one side. I only have to polish it. It only has to be geometrically perfect on one side. When I make a lens, it has to be geometrically perfect on both sides and nice and smooth. It has to be just right. And when I pour this glass, I can't have any little bubbles in it. The bubbles would not be good. It's much more difficult. With this, it doesn't matter if there's bubbles in here, because I'm going to coat it with something anyway. All I care about is the surface of that. So the mirrors, the bigger mirrors, are much easier to make than the lenses. The mirrors are easy to support accurately from behind. If I'm building a telescope, you saw the construction of it. When I build this and I aim this telescope and I aim it at the sky, here's all the weight down here. If the weight is down here, I have a support structure here. It's a lot easier to support that. With a refractor, here's the big lens, and I'm trying to support all of the weight that's up here down here. And so this thing would tend to move. It's harder to support the weight, and the bigger that becomes, the more difficult that becomes. It's also easier to, I said that one first. It's also easier to support the mirror. In other words, structurally, when I mount this mirror, it's much easier to hold on to this. I could hold on to it anywhere along here. But with a lens, I have to hold on to it only at the edges, only around the edges, and that becomes difficult mechanically. And then the folding action of the primary and secondary mirrors, the fact that we can fold light back and forth, provides our magnification rather than a straight tube. So the larger the telescope becomes, the longer it becomes if we want magnification, and it just becomes much more cumbersome and much more difficult. Whereas you saw when we can fold the light in the Cassegrain and the Newtonian, we could build very large telescopes, but they're not very long because we're folding the light and still getting a lot of magnification. So sounds like a great test question. We'll go from there. All right, which one is which? Well, that one's the refractor, the big lens at the front, the optical lens in the back, and the mount. And here is a reflector telescope. There's a mirror back here. And up here is where the eyepiece is. The light's coming in here. It's bouncing off of here, being reflected back. There's the eyepiece there. And it has some mounts on here that follows as the Earth moves, you can set it to follow that planet. And so if you don't have one of those, then you have to keep moving your telescope to follow whatever it is that you're looking for. With a mount like this, with a motor drive, you could set it towards that planet, and it doesn't matter. It will keep moving with it as the Earth is turning. Hubble Space Telescope, put this up into space so we could get away from the atmospheric interference that we get from the atmosphere. And it's been up there for many, many years, and it can see way, way out there. You've probably seen lots of pictures from the Hubble Space Telescope. These are different non-optical telescopes. This is the Arecibo radio telescope in Puerto Rico. This is on my bucket list. I would love to go and see this. It's a big hole in the ground where they built, and all this is just a bunch of metal plates, and it bounces radio waves off onto this tower, and then that just looks in different directions, and that's how they can aim it. This is a radio telescope here. CCDs, this is a charged coupled device, essentially television. Nowadays the light just comes in and hits these things like your camera and your motion picture camera and your cell phone and everything, and it converts it, rather than optically, it converts it directly into digital information. It goes into the computer, and we can analyze it that way and manipulate it in lots of different ways. Here's an ultraviolet detector that's on the ground. Even though we can't get a lot of ultraviolet detection, what we'd be looking here is probably the sun. This is IRAS, the the Infrared Astronomical Survey. This is up in space now. It may not be working anymore, I'm not sure. But this is one of the first spacecrafts we sent up to look at the universe and our galaxy in infrared, which we could not see from here on the ground because of the atmosphere. And here is looking at, this is visible light. Here's Orion in visible light, and here is Orion in infrared. Notice that out here we got a lot of bright stuff here in infrared. In infrared light, there's a lot of infrared light over here. When we look over here, we don't see much at all. There really isn't anything there. In other words, by looking at the universe and the galaxy in infrared light, we're seeing objects and seeing much more of our universe than without it. And we can tell, well, there's something going on out here. There's some objects out here that are emitting in infrared, and mostly in infrared, which means they're cooler than most objects, but there is something there. Here is a picture of the center of our Milky Way galaxy in infrared light. And we can't look directly at the center of our galaxy with visible light, but because there's a bunch of dust clouds in the way. So light would be absorbed by the dust cloud. So we can't see, just like any dust absorbs light, we can't see behind it. But infrared passes through it. So we can analyze the center of the galaxy with infrared light. Here's Andromeda Galaxy in visible. Here's the Andromeda Galaxy in X-ray. We're looking at the X-rays that are coming from the Andromeda Galaxy, and you can see that the center of it is giving off a lot of X-rays. That tells us a lot about it. Typically it means that there's probably a black hole in the center, and we're looking at a lot of these places with other spectra, and it's going to tell us a lot about these places. This is the Milky Way in infrared. You have to understand we are inside the Milky Way, so this picture actually wraps around us, and it's been flattened out. And so this is looking all around us at the Milky Way in infrared, and rather pretty picture there. These are other galaxies, and we're looking at them in ultraviolet rays. Ultraviolet is very high energy, so what we're looking at are very high energy sources inside these galaxies. And it tells us a lot about the kinds of stars and the kinds of objects that are there. Quickly, binoculars. If you have a pair of binoculars, get a good, nice pair of them, and you can to look at things, objects in space. They're really pretty good because they give you a wide field of view, but they give a good magnification on it. And essentially, what happens there is the light's going to come in on the objective lens. It bounces through two prisms and goes out that way. That's why they're shaped the way they are. If you want a good pair for astronomy, you'll notice that it'll say 50 by 20, say 50 millimeters by 20. What they mean is that the objective lens is 50 millimeters and it has a 20 magnification on it. So the higher both numbers. The 50 millimeters, you want a larger number here. Why? You want a large objective lens. It's gathering more light. So if you want a good pair to look at the sky with, essentially you're looking for the highest numbers. 50, 20, 70, 40. Well, that would be a really nice pair. 70, 40 would be a very nice pair of binoculars. So the higher the number, the more magnification, the better for astronomical applications. The end. We're done. And we did a lot about light. Now this particular unit, it's in our first unit. There are some test questions that are coming off of this for our tests. But remember this stuff because we're going to go into the next unit and we're going to use these tools here to study our next unit about the universe and stars. We're going to use this quite a bit. So it's not that we're done with it. In fact, when we get into the next unit, we're going to be reviewing this stuff briefly. Recall that we have Wien's law, we have Kirchhoff's law, we have the different kinds of spectra. In Kirchhoff's law, we have the absorption, we have continuous, and we have the bright line spectrum or the emission line spectrum. Wien's law tells us that the higher temperature something is, then the higher the peak frequency, or rather, we can look at an object and measure its highest peak frequency. That particular high peak frequency tells us what the temperature of that object is. So we know the temperature of these different stars based on their spectrum. And about telescopes and why reflector is better than that. So in conclusion, this concludes this part of it, and we'll pick this stuff up in the next unit and just retain some of this stuff because we're going to use it again and again. Thank you very much. This has been PSE 2121 and the unit on light. Thank you.